Yeah. Yeah, okay. Yeah, we've got Ashley Cooks again, who was introduced a few days ago. She's at MPI PKS and MPI, the other one next to it.
CPFS.
Yeah, lots of letters, all the things interesting.
Yeah.
Anyway, and she's an expert in topological phases and new topological phases and cool stuff, and we're going to hear more about it starting now.
All right, so in the first talk, basically, I was telling you about some recently introduced topological phases of matter just for electronic systems in equilibrium, kind of moving away from the, I guess, current approaches or like efforts to search for previously unidentified topological phases of matter in the effectively non-interacting regime, which have more recently focused a lot on, characterizing topology associated with like different crystalline point group symmetries in the case of electronic systems, or characterizing various analogs of electronic topological phases, the mechanical topological phases, the Floquet, the non-Hermitian. Even in electronic circuits, people have been characterizing topological phases. So this talk today is about models that realize this sort of physics, specifically that are also like describing transition metal oxide superconductors, and specifically those models with non-negligible atomic spin orbit coupling, because as I will show, it's extremely important in realizing, I'd say, the more interesting topological phase diagram, topological phase transition that's possible in these systems. So just as a quick reminder, yesterday I just, gave you some motivation and.
I'm going to put down the screen.
Okay.
Can we switch to speed icons?
Oh, no, that's this.
That might have been me.
I don't think.
This is just the lights, right?
Yeah, we'll leave the lights on there. Yes, we've got the blinds down.
Now you need to.
Oh, VGA, can you switch it to HDMI?
Yeah, go ahead. You can't. We need the lights. We need the lights on the blinds down. Otherwise, it's a bit crazy.
All right, so yesterday, basically, I was giving you some motivation and background, and then I was introducing you to the toy models for these phases, which you can realize just as four-band block Hamiltonians. And you can also realize Bogoliubov-de Gennes four-band block Hamiltonians that capture this sort of physics. And I introduce you to the two-dimensional and three-dimensional versions. And specifically, I needed to tell you about the three-dimensional versions so I could tell you about one of the bulk boundary correspondences. And before I move on, I just wanted to explicitly make the following point. So for people who are from like a kind of cuprates, high TC superconductivity background, they might be much more familiar with characterization of systems based on mappings from a Fermi surface, basically, to some space of some observable, some order parameter. I'm not talking about those kinds of mappings here. I'm talking about mappings from the full Brillouin zone, basically, to, in this case, like the space of spin, rather than the space of projectors. So today, I'm going to tell you about the realization of what I call the chiral topological Skermion superconductor phase and the helical topological Skermion superconductor phase in a very established tight binding model for superconducting strontium ruthenate with spin triplet pairing. Now, I know that experimentally people have been moving away from the spin triplet picture because of night shift experiments and their results. But the key point is just to demonstrate that in a model that we've been considering, I think in this case for about 2 decades, this physics was lurking there all along. And then I'll be able to tell you about 2 different kinds of topological phase transitions that occur for these Skermion phases, because they actually occur for this tight binding model of strontium ruthenate. And importantly, and maybe I got a little too into it in the first part, but basically to try to get people interested in the second part, I was telling you a lot about the fact that, the type 1 topological phase transition is like what we expect, what is standard for effectively non-interacting systems. But there's also this type 2 topological phase transition that occurs in effectively non-interacting systems while respecting the symmetry protecting the topological phase. And this has important consequences that I will discuss at the end. Okay, so sorry, this is actually for Piers, and Piers is apparently not here, but he had asked for the tight binding model, basically for the 3D Skermion phase. So, and specifically then that meant I needed to tell him about the tight binding model for the Hopf insulator. So it takes the following form. You have this sort of like a vector Z, where like Z up and Z down take the following form. So these, correspond basically to kinetic terms. Sorry? Oh, okay. All right. So maybe we'll wait a second. All right. So this slide was specifically for Piers, basically. So you asked about the tight binding model for the 3-dimensional Skermion phase that I talked about yesterday. And that meant you were asking partly about the tight binding model for the Hopf insulator. So basically, the block Hamiltonian takes the following form in terms of this is the vector of Pauli matrices, and this is some vector nu, where the different components of nu can be expressed as follows in terms of this Z and the different Pauli matrices. And Z basically takes the following form, where here I just, took an expression basically out of work by Joel Moore and others, where they were just, they fixed the value of like a mass term here to be 3/2, but the point is that more generally, this would be some like term M that you could use to tune through topological phase transitions in the system. And I was combining this with its C prime partner on the block diagonal. And then I was adding spin triplet pairing that took basically the following form, where in my case, like the delta L was just like a delta naught, a superconducting pairing strength. And I was considering the following D vector. And then the key point was you would take, so the boundary conditions that I was talking about, just to make it clearer, because there seemed to be a bit of confusion associated with this as well. The idea was that you take open boundary conditions in the X and Y directions, and then you replace KZ with arctan of Y minus X, I think, basically, to serve as some angle characterizing the defect in the center of the system. Okay, so now I'm talking about, yeah?
You're sharing the wrong screen on Zoom.
Okay. Okay, I see. 1 second. Stop share. And I have to get out of this, and then I have to, nice. Just cover that up. And where is my cursor? Go back here and share screen and share Keynote. And now your screen sharing is paused. Screen sharing, Keynote. It says my screen sharing is paused. Sorry? So people can't see it, can they?
It's still the wrong one shared for some reason,
Mm-hmm.
but they can see it on Zoom.
Yeah, but basically fix it. Oh, I see. The recording's gonna go out like that too.
Okay.
choose to share keynotes instead of desktop show the presentation.
Maybe I'll try this. How about now?
Yeah, that works.
Oh, okay, great.
Perfect.
All right, so I added this slide in as well, just to kind of really make it clear. I'm considering an established model that I think was first introduced by Manfred Sigrist and others, although I'm writing the version that is in this paper by Masatoshi Sato and co-authors. But basically, the tight binding model consists of these kinetic terms, which include, and I'll discuss the model schematically as well in a following slide. But basically it has the following intraorbital kinetic terms, the following interorbital kinetic term, I think between like YZ and XZ orbitals. Yeah, we're in a basis of the T2G orbitals and for the normal state, and we have a spin half degree of freedom. And then there's an additional atomic spin orbit coupling term. And then finally a pairing term where the gap function for a given orbital takes the following form. And then this delta L is taken to be the same for each of the different T2G orbitals. And again, I'm considering the D vector that in this paper was discussed for the high field phase. So when some applied Zeeman field, which was another term actually in the model, but when the applied Zeeman field was greater than 20 millitesla. So this is just like a schematic overview of what I was briefly telling you. So here are the interorbital hopping terms. Here's the interorbital hopping term. There's also an atomic spin orbit coupling term because of the 4D ruthenium ion, and also the applied Zeeman field, and a chemical potential term, and an orbital energy offset between the XY orbital and the XZ and YZ orbitals. And it becomes relevant later, but here is the normal state mirror operator for taking Z to minus Z. And in this case, I'm focusing, so for this quasi two-dimensional system, I'm just considering a two-dimensional model. And here's the spin triplet pairing, as I mentioned previously. And the key point here is that this model has the generalized particle hole symmetry that I told you about previously, which acts in almost the same way as C, except you do not take K to minus K. And it also has, for the Bogoliubov-de Gennes Hamiltonian, a mirror invariance under the mirror operation tilde mxy minus, which I'll tell you what that is. So basically, if your normal state has the mirror symmetry, basically, upon taking Z to minus Z, then there are two different options for the counterpart mirror symmetry that the Bogoliubov-de Gennes Hamiltonian has. And it depends on how the superconducting gap function basically transforms under the normal state mirror according to the following expression. It can be even or odd under this normal state mirror. And basically then there are two different possible expressions that the Bogoliubov-de Gennes Hamiltonian could satisfy, where basically this tilde mxy plus or minus takes the following form. And the key point is, it's possible when you have the tilde mxy minus to have each of your mirror subsectors to inherit basically this generalized particle hole symmetry from the full system. And then we can do something really cool, basically. So we can go to the basis in which, take the Hamiltonian to the basis in which that mirror operator is diagonal. The Hamiltonian becomes block diagonal. And then we can think about computing a Skermion number for each of these mirror subsectors. And then you can have two different interesting possibilities at least. So one case is where you have a non-trivial Skermion number in one mirror subsector and trivial mirror Skermion number in the other. And this is basically, just one Skermionic texture. So this is like what I was telling you about in the first talk. And it's like a generalization of a two-band churn insulator. And so I call it the chiral topological Skermion phase. So in the first talk, I was just talking about chiral topological Skermion phases. And then there's another really cool case where you can have a non-trivial Skermion number in one mirror subsector and minus of that Skermion number in the other mirror subsector. And I call this the helical topological Skermion phase because you can think of it as basically a generalization of a quantum spin Hall insulator. If you think about the fact that you can construct a quantum spin Hall insulator from a churn insulator and its time reverse partner. So the bases for these different mirror subsectors are quite important in identifying the forms for the spin operators that you will use to try to compute the Skermion number. So they're quite interesting. So one thing is I'm putting the daggers first because that's just naturally what happens upon block diagonalizing the Hamiltonian. And then another thing that's really interesting here is you have a basis of like spin up, spin down in one sector, and spin down, spin up in the other sector. And one thing I'd like to point out that's really interesting is that the fact that you get like, you don't just get spin up in one mirror subsector and spin down in the other, results from the fact that the XY orbital actually transforms differently under the mirror than the XZ and YZ orbitals. If they all transformed in the same way, then you would get like basically quite boring physics. So now that we know the basis, we can try to write down the spin operators. So again, I said that as a result of just naturally, as a result of the block diagonalization process, you get the dagger operators coming first. So I just wrote the operators in this form rather than as like SI minus SI dagger, as I was showing you in the first talk. And then the key point is for that very interesting basis, you can write down the spin operators by constructing the raising and lowering operators that you need in this case, which then allows you to construct the SX and the SY operators. And then you can use commutation relations to get the SZ. So in this case, you have to think about being able to raise from either spin down to spin up. And then you also have to think about actually possibly just kind of shifting sideways from one spin down to the other spin down. But you have to, the key point is also that you don't have a full SU2 subalgebra for the case of the two spin downs. And so when you actually construct SZ, you construct it basically from a linear combination of the commutation relations only for the full SU2 subalgebras, which gives you the following form. I'm ignoring constant like prefactors here. So that's for one mirror subsector. And for the other one, basically the raising operator in the first sector is kind of like the lowering operator in the second. And so you get some changes in sign basically for SY and SZ. And from that, we can compute the ground state spin expectation value texture over the Brillouin zone. Here I'm assuming half filling, and we can also compute a total churn number basically for each of the mirror subsectors. So I'm just showing you for, one subsector and for the other. First the total churn number, and then the Skermion number computed with the operators that I showed previously. And so there's a lot. And here I'm using basically the parameter set that was used in the Masatoshi Sato paper to describe strontium ruthenate with the spin triplet pairing. Although here I'm constructing phase diagrams by allowing the atomic spin orbit coupling strength to vary, as well as the applied Zeeman field. Just because based on our experience, maybe from studying quantum anomalous Hall insulators, these are two knobs that we would expect to yield a lot of like interesting variety in terms of the topological invariance. Okay, so there are a lot of differences basically between the two phase diagrams. Maybe first of all, I'd like to point out that the chiral phase is actually where the coordinate set previously used to describe strontium ruthenate lies. So that's interesting. Another thing is that the helical phase does seem to appear, although in this case, I am holding the pairing strength fixed at the value that was used for strontium ruthenate. And of course, what we realize is as you increase the applied Zeeman field strength, you expect to gradually destroy the superconductivity. So I'm not necessarily saying at all that this is experimentally accessible. I'm just saying that it's very interesting that in a physically relevant tight binding model for transition metal oxide superconductors, you do actually see this phase. And then there are other things here. For instance, it looks like there's a continuous phase transition in the Skermion number. So I will tell you what's going on in that case, but it does not, mean that it's not possible to have topologically stable phases where you have integer quantized Skermion number, which you see basically in other regions of the phase diagram. I think one last thing I would mention at this point, very interestingly, you can have regions where the total churn number is 0, but the Skermion number is non-zero. So you really see much more so than what we saw at the 4-band level, the decoupling and the independence basically of the Skermion number from the total churn number. They really are acting as separate topological invariants, characterizing separate topology. So this is just, I just wanted to show some representative Brillouin zone spin textures for one of the mirror subsectors here. So this alpha, beta, and kappa are spin textures for the following points in the phase diagram. So one thing that's interesting here is you see that for alpha and beta, you have like a single charge 2 Skermion. And then at kappa, you see what looks like it might be like effectively a charge 2 texture resulting from 2 charge 1 Skermions. Although it, as I said, there's something interesting that happens here that leads to the continuous phase transition. And so basically it's not a full Skermion. I'll leave that as like a hint as to what's going on. But very interestingly, you see that the churn number is always even in this phase diagram, at least when it's stable at an integer value. So this is a reflection of the fact that the normal state Hamiltonian for strontium ruthenate and also for the mirror subsectors is even in K, which as we saw previously corresponded to, at least in the 2-band model, corresponded to an even churn number. So everything's kind of checking out in this sense. So now I can get into talking about the topological phase transitions. One, I think it's, so how do I say this? If we go back to the total churn number phase diagram and the Skermion number phase diagram, and we compare them, we would see certain lines along which we see the total churn number change and also the Skermion number change. And this basically is corresponding to a type 1 phase transition for the Skermion number. Basically, there's a closing of the superconducting gap across those lines in phase space. But I really want to show you the more interesting case here where I'm considering a cut through lambda equals 0.3, and I'm varying the applied Zeeman field and just checking on what happens to the Skermion number as I tune the applied field. And basically what you see is the Skermion number jumping in effect from one integer value to another. I would note here that at the time I was using more inefficient methods for computing the Skermion number, and in the second paper that's on the archive, I discuss far more efficient methods for computing the Skermion number. If you zoom in on that transition, you see some wild fluctuations as a result of the numerical, like the slow convergence basically of the Skermion number calculation. But you do see very nice quantization on either side. And if we compare this to the plots of the minimum direct gaps along this cut, what we see is that none of them, this is for say the minimum direct gap between say the lowest energy band and the second lowest energy band, and then also between the second lowest and the third lowest, and then also the superconducting gap. All of the ones that we might expect maybe we'd expect one of them at least to close, considering we're looking at an effectively non-interacting system, and we're respecting the C prime symmetry, but basically none of them close. So this is an example of the type 2 topological phase transition that I was telling you about. If you're a little concerned also about these fluctuations indicating that maybe this is not, really a topological phase transition or something, one thing that I could also show you is basically the plot of I call it the spin curvature, basically the integrand of the Skermion number over the Brillouin zone, just to either side, basically, of the phase transition. And what you see is not much changes across the phase transition, except for these two features highlighted by arrows that are also symmetry related. And so what you see actually is a neck on one side of the phase transition that breaks upon crossing the phase transition. So it's really like, even though there are all these like fluctuations, really it's like a particular value of applied Zeeman field where something very violent is happening. So to understand better what's going on in this case, we can zoom in on those little patches of the Brillouin zone in the vicinity of the topological phase transition, and we can plot the unnormalized ground state spin expectation value texture. So this is the like SX, SY, and SZ components. And basically each of them is passing through 0 here. And actually, if you overlay them, there is a region where they all appear to have gone to 0, like at the same point. If we plot the normalized ground state spin expectation value texture in the vicinity of the transition, what we see is actually there's a particular point in K-space across which basically the derivatives at that point in the normalized ground state spin expectation value texture with respect to momentum becomes singular. And this is what destabilizes the Skermion number in this case. So the key point is basically what's happening here is we have non-negligible atomic spin orbit coupling in this system, and we have an orbital degree of freedom because of the T2G orbitals, and we also have our spin degree of freedom. Spin is not conserved, and basically at this phase transition, what is happening is the total angular momentum is flowing entirely into the orbital sector, which can occur without the closing of energy gaps. And so you might be concerned, or you might still be confused, what is ensuring that the Skermion number is stable, and what goes wrong that leads to allows you to have the Skermion number basically change from one integer value to another. So the Skermion number is stable if your spin, as I was saying before, but I'll say it again, if your spin is finite in magnitude everywhere in the Brillouin zone, the idea is that then you could tune your system by some like parameter epsilon, and you're always guaranteed that you can have some like sufficiently small but finite epsilon such that maybe you change the magnitude of the spin vectors at different points in the Brillouin zone, but none of them went to 0. So basically the Skermion number is invariant under sufficiently small perturbations, which is our very broad and loose idea of what a topological phase is. The key point is that you then destabilize the Skermion number by having the spin go to 0 in magnitude. And the key point is this can happen in 2 different ways. So the first kind is with the closing of an energy gap. But if you have non-negligible atomic spin orbit coupling and an additional suitable degree of freedom, then you can also have it go to 0 without the closing of an energy gap. So here, I'm just showing you that topological phase transition in some additional detail. So basically on one side of the transition, you see 2 features in the spin texture, like one basically in the in-plane texture and one in the out-of-plane texture. They're basically occurring at different points in the Brillouin zone. So basically, there's the texture or the feature in the in-plane component is basically a point across which you see the in-plane component reverse sign. So it might be starting like this, and then across the point, it goes like this. And then there's a point as well in the Brillouin zone across which the out of plane component changes sign. And basically, as you move towards the topological phase transition, these two features move towards one another. And at the topological phase transition, they coincide. And then after the phase transition, they have been interchanged. And so this is, of course, if they all, if the points coincide, that means all three components of the spin have to pass through zero in order to change sign. And this is, part of why the spin is going to zero at this point and resulting in this topological phase transition. So this is a cartoon picture of what I was showing you just a moment ago. The idea is that there was a point across which the in-plane component was changing in sign, and then there was another point across which the out-of-plane component was changing in sign, and they actually moved towards one another along a line. And then at the phase transition, they coincide, and the magnitude of the spin goes to zero without the closing of any energy gaps. Again, I'll say it, in an effectively non-interacting system while respecting the symmetry, protecting the topological phase. And then after the phase transition, basically, they have been interchanged. So can we get a little more intuition for why that might lead to a change in value of the Skermion number? So one cartoon picture that I think is helpful to some extent is you can also think about an effectively 1D winding number. Here I've just put it on a cylinder. And you can think basically about such features occurring in this 1D winding as well, basically points across which the in-plane component changes sign and points across which the out-of-plane component changes sign. And then we can imagine starting with a winding on the cylinder that's non-trivial. Basically, we wrap the cylinder twice. And then we can ask what happens if we interchange two of these points, say in the second half of the cylinder. And basically this forces the winding number to change, which you can kind of see if you actually try to draw out a line now that you have interchanged these points. So basically it makes some sense, even at this level, at the level of this cartoon picture, that if you interchange these features, you expect a change in the winding of the Skermion. All right, so one other thing I promised I would talk about was that continuous phase transition in the phase diagram. So the key point is, okay, so basically I'm showing you the unnormalized spin texture components along for fixed spin orbit coupling and as a function of applied Zeeman field. And basically what's happening is as you're increasing the Zeeman field starting from a region where the Skermion number is 0, you jump up to what looks like a Skermion number of 2. And these two little Skermions appear. And basically what happens is there's a hole in the spin texture at the center of the Brillouin zone. And these two little Skermions move towards one another and just disappear through the hole. And so what you're seeing is the fact that the system had a hole in its spin texture. The spin magnitude was 0 at the center of the Brillouin zone throughout that transition. So we weren't looking at a case where we expect to see integer quantized Skermion numbers. And actually what the system was doing, I think this is quite interesting personally. The system was forming what I call an almost Skermion, which I also talked about in the case of the toy models. But here it's this really kind of cute picture of the two little Skermions kind of coming together and disappearing through the hole in the center of the Brillouin zone. All right, so I said that I would talk a bit more about the implications of the type 2 topological phase transition. So the key point is that it serves as, to my knowledge, the first contradiction of what's known as the flat band limit assumption. So this is the assumption that, let's say, and I said it in the first talk, I'll say it again. Let's say you have some Hamiltonian with dispersive bands, some number of bands are occupied, and basically you have some set of invariants. So again, for people who maybe think about simpler cases, maybe you will think about just like one topological invariant characterizing the system. And as I said, things are more complicated now, and you in some cases have to think about more than one topological invariant characterizing the system at a given point in phase space. So imagine that you have some set of topological invariants for this Hamiltonian with dispersive bands. So the assumption is that if we adiabatically deform this system to a flat band counterpart, so without closing this energy gap, without changing the occupancy of the bands, and while respecting the symmetry protecting the topological phase, and if this is an effectively non-interacting system, then we're guaranteed that this counterpart flat band Hamiltonian has this a set of topological invariants that's the same as for the dispersive Hamiltonian, and the value for each of those invariants is the same as it was for the invariant counterpart for the dispersive Hamiltonian. So the key point is the flat band limit assumption has actually been used very widely in study of topological condensed matter. So for instance, it's used to connect the spectrum of the physical Hamiltonian to the spectrum of the entanglement Hamiltonian in order to use the entanglement spectrum as a diagnostic for topology in the physical Hamiltonian. It's used in computation of Wilson loops that basically to avoid gauge fixing problems. You basically express the Wilson loop as an integral over projectors. And it's also used in the construction of the tenfold way classification scheme. And another, I've seen, so I think I mentioned it briefly at the end of the last talk, but one of the earliest examples that I'm aware of where they used the flat band limit assumption was actually this paper by Avron, Seiler, and Simon in 1983. So basically they talk about, the idea that you have some number of bands occupied, and you can think about computing Chern numbers for each of those bands, and you think about summing them to get a total Chern number that characterizes the topology of the ground state. And they basically try to argue for the idea that if you deform the system such that two bands of this occupied set touch and then come apart, even if their individual Chern numbers change, the total Chern number does not. So what happens in the Avron, Seiler, and Simon paper is they tell you, we will give you a rigorous proof in a future work. They cite themselves, and that paper never actually appeared. And instead, they use the flat band limit assumption in the meantime to argue for this. So I basically, it seems like we should at least figure out where exactly we've used the flat band limit assumption, and reconsider when it was actually safe to do so, because basically even in the effectively non-interacting regime where we thought it always held, it does not hold in general. And more generally,
Can I just ask a question?
Yeah.
Because there's always a way to make the band flat while keeping the eigenstates exactly the same.
Okay, no, that does not involve an adiabatic deformation that guarantees that the value of the topological invariant stays the same. It is used to argue that the homotopy group of the flat band Hamiltonian is isomorphic, basically, or maybe it was just homeomorphic maybe, to the homotopy group of the dispersive Hamiltonians. But related to that, one thing that I'm realizing now is I think it was, basically the topology of the Hamiltonian is not fully contained, I don't think, in the Hamiltonian itself. To some extent, it's also contained in various observables associated with the Hamiltonian.
And you can get them from the Hamiltonian, so I think that's a philosophical statement.
No, basically, and it's something I'm thinking about still right now, but basically there seems to be evidence of extension, basically, of the topological classification for Hamiltonians by this spin topology. So basically the homotopy group of the projectors, it seems as if it's possibly giving you part of the topological classification, but not all of it. And really, you need to think about the homotopy groups associated with the different observables that you could compute with the eigenstates of the Hamiltonian.
Even so, so what you're saying is it's nothing to do with making the bands flat, changing the energy eigenstates, okay, but it's adiabatically deforming the eigenstates. We should be careful about. There needs to be more consideration about.
Okay, so basically, I much more firmly am telling you, we need to be careful about when we try to like use this flat band limit assumption, when we try to adiabatically deform our Hamiltonian to some other counterpart and argue that the topology is the same. Much less firmly, I'm still thinking about it. I think you may need to think about extending the topological classification of the Hamiltonian as well, beyond simply the classification given to you by the homotopy groups associated with mappings from the full Brillouin zone to the space of projectors.
Yeah, I think that I've sort of got that. But I think it's just nothing to do with changing the energy levels. It's all to do with how you're adiabatically deforming the eigenstates.
Well, the flat band limit assumption is.
Well, yeah, but that's part of it, but just try to get what it is in this, because the way you're presenting it, it seems like it's making the bands flat is the problem. But I don't think it's anything. To do
So
with them
the
being
problem
flat.
here is that you could do exactly this sort of, thanks for asking this, because I think it's important to maybe say it this way. The point is you could do exactly this sort of deformation and the Skermion number could change during this process,
Yeah,
even though you didn't close the energy
because you're
gap.
changing the eigenstates. You're making an adiabatic deformation. You can make an adiabatic deformation.
But that's
while keeping the energy the same. I think it's nothing to do with
So-
how the energy is.
So
changing.
no, that isn't an adiabatic deformation. It's actually discussed in the Avron-Seiler-Simon paper that all that is an argument to try to relate the homotopy group associated with the full Hamiltonians to the homotopy groups associated with the projectors. And this doesn't actually include an
Okay,
adiabatic
here's the
deformation.
question then. Where does the energy come in your definition of Skermion number?
Where does the energy
Yeah,
come in?
Because what you're telling me is what I'm saying is that changing the energy really matters. In which case the energy must come into the Skermion number somewhere.
I showed you the expression for the Skermion number.
Yeah, which seem to involve the eigenstates and what the eigenvalues.
Yeah.
The
So-
energy is the eigenvalue, so the energy doesn't come into it.
Not directly, except that certainly if you close, say, the superconducting gap, you will
Yeah, sure.
destabilize the Skermion number as well.
Yeah, but that's because you can no longer uniquely define the eigenstate in some ambiguity.
Mhm.
Because of the degeneracy. That's fine, that's clear, I think.
Yeah, I think I'm still confused about exactly what your concern is, or what you're trying to
I'm just trying
stay.
to understand what it is about the flat band limit, and I think it's nothing to do with it being flat or changing the energy levels. I think you can sort of separate that out and say, okay, of course I can't make things degenerate because then I can't define uniquely an eigenstate. But what you've got to be very careful about is what else you have to not close, like a spin gap or something, when you're deforming the eigenstates.
Yeah, so you could
So
think of
that
it that way, that so you could think about this deformation perhaps, and then adding in, but also we don't have the spin gap go to zero. Which
and
then
then
leads
what
to
you're
an
saying-
issue of like, what other gaps do we have to worry about? But certainly this deformation by itself, yeah, it's not the issue. The problem isn't necessarily that you made the bands flat.
Yeah.
The point was you thought that in doing some deformation where you didn't close the gap, you did not change the topology of the ground state, but actually you can change the topology of the ground state. And the problem is that people do this sort of deformation. They happen, what is computationally convenient for them is to work with the flat band Hamiltonians rather than some other Hamiltonian that they've arrived at through some adiabatic deformation. But the point is that they might have changed things basically during that process, even for effectively non-interacting systems. We already knew for interacting systems that this assumption did not hold in general.
No, there I'll agree, but I think a lot of the papers and recent proofs as well only they don't require any adiabatic deformation. They only have one of them, and you can do one of them where nothing will change.
They only have one of them.
They only need one of them.
One of what?
A deformation to flatten the backs. They're just sort of getting rid of the structure.
I really
We can
think
discuss
that,
it
no, okay, so I'll just,
It's going to depend on exactly which proof. But
yeah, so I'll say again that it's actually kind of discussed, I think, fairly nicely in the Avron-Seiler-Simon paper. This idea of just deforming eigenvalues and not doing anything to the eigenstates. And that is not an argument for having the same set of values for topological invariance at the end of your deformation that you started with. They only use that to argue for the topological classification. That's it.
I'll agree with that. I think we're basically agreed.
Yeah, I think so. All right, so I actually, maybe I don't know how much time I actually
There's
used.
still some time for questions.
All right. Anyway, this is my summary slide. So the key point is that Skermions in your momentum space spin texture, instead of your, or in addition to a projector texture, are possible for block Hamiltonians with this C prime symmetry, where these spin Skermions are, independent from the projector Skermions for the case of n greater than 1. And so this topology is at least relevant to centrosymmetric superconductors because this generalized particle hole symmetry, the operator for that can be expressed as the product of the particle hole operator and the spatial inversion operator. And you have each of those symmetries individually in the case of centrosymmetric superconductors. So then you also expect the product to be present. And basically models for transition metal oxide superconductors can realize some of these topological Skermion phases matter. So I told you about the chiral case and the helical case, which you can think of as generalizations basically of a Chern insulator and a quantum spin Hall insulator, respectively. And finally, there are two different kinds of topological phase transitions that can occur in effectively non-interacting systems while respecting the symmetry protecting the topological phase for the Skermion number. So type 1 is when the spin basically goes to 0 with the closing of a bulk energy gap, and this T stabilizes the Skermion number. And type 2 is when the spin goes to 0 without the closing of a bulk energy gap, which, basically, I attribute that to the combination of non-negligible atomic spin orbit coupling and some additional suitable degree of freedom, like an orbital degree of freedom, such that the spin that is not conserved in this case can go to 0 without the closing of an energy gap, because your total angular momentum can flow entirely into the orbital sector without the closing of an energy gap. Another interesting thing here is because of the crystal field splitting in the system, we don't have quantization of basically the topological charge, or we don't have a quantized topological charge associated with the orbital angular momentum. It's actually unquantized. And what is not clear to me yet, and I'm very interested in exploring it further, is what sorts of consequences are there of the fact that, maybe you can think of the orbital sector as a sort of like non-topological or trivial reservoir into which topological charge density can flow from the spin sector. This is something I'm still quite interested in. And basically what I was telling you at the end, and I do not understand the full consequences of this. I am just trying to tell you that this type 2 topological phase transition contradicts an assumption that we have used basically very broadly over the course of the past 4 decades. So that gives you some sense of how important it may be besides thinking about the fact that this physics occurs in centrosymmetric superconductors, so we may need to think a bit more about the consequences of this topology having in principle being in models that we had considered previously, but we weren't aware of it. There's also, the issue of whether this topology associated with subsets of the degrees of freedom of the ground state, there are potential consequences associated with this sort of topology just in study of topological phases of matter as well. And with that, I'd like to thank you for your attention.
Okay, plenty of time for discussion and questions.
How many values can the difference of the Skermion number and the Chern number take?
You like, how independent are they?
I guess, yeah. I mean, can the Skermion number be very different from the Chern number, or does it stay within one or two?
So I haven't fully explored this issue. So I don't know how independent it can be, but what I can say is certainly you can have cases where the total Chern number is 0 and the Skermion number is non-zero. And yeah, there doesn't seem to be, so at the 4-band level, there is a very tight relationship actually that I have seen so far, basically of the total Chern number being minus, this is for half filling, -2 times the Skermion number. But beyond that, it appears as if they decouple completely, but there's more work to be done in understanding the extent of this.
But for like, if you had a lot of bands, say, if for n greater than, I don't know, 4, does there still need to be a point in like phase space where they need to coincide, Chern number and Skermion number?
Like be equal?
Yeah.
So no, there's no guarantee at all that you would have to have a point like that in the phase space. There isn't that guarantee or requirement, even at the 6-band level, which is basically what I was considering. So the Bogoliubov-de Gennes has a 12x12 matrix representation. And then upon block diagonalizing, I had 2 6x6 matrix representations for the 2 different mirror subsectors. And basically each of those, that was what I was considering there, the n = 3 case. Even at that level, there doesn't seem to be this sort of a restriction.
Quite low physically in the system. We can't get very high fields. State, whereas in the XY plane, H2 is much bigger. And there is this extra phase that's been seen, and I think it's been discovered recently. Some people are now saying it's a current phase, but it could be some other, topological phase of transition or something. Quite large in-plane field. I don't feel in-plane field, is that the topological classification still work?
I think the key point is you, at least for this topology in mirror subsectors, you need to have this tilde mxy minus. And for some D vectors, you don't have it. Actually, this is discussed in the Masatoshi Sato paper. So in that case, you would, maybe still be able to find topology associated with the full system. But in that case, you'd consider different expressions for the spin operators. And I haven't explored that.
Can self similarly repeat this construction? So now let's say that with 4 bands, you can have a spin Skermion number, which comes to 2 subbands. So let's say you double the number of bands. If you do this again, more complex symmetry. So you have, say, spin Skermion number. So now it's actually another topological invariant underneath.
Yeah, so in principle, I mean, I was talking about spin, but you basically have to check for like each of your degrees of freedom, and perhaps combinations of them. You have to check on whether you have a non-trivial homotopy group. So this is, you can definitely take it in that direction. Someone has to, I think, basically exploring the topology associated with other degrees of freedom. And of course, related to this, you can extend this, physics to like interacting systems or the various analogs of the standard electronic phases. So like all of these different branches that have descended from like our study of electronic topological phases in equilibrium. We expect analogs of this sort of physics in each of those cases as well. Yeah, and in the case of the Forbun model, actually, you could compute a Skermion number for the orbital angular momentum, or sorry, whatever in that case, I think you should really just think of it as the generalized particle hole degree of freedom. Yeah, so sometimes your other degrees of freedom could have non-trivial topology, non-trivial classification, and sometimes not. And so I've just thought about this basically for a couple of days so far, but what I was thinking was, the tenfold weight classification, it comes from attempting to classify Hamiltonians according to symmetric space. So this is work going back to Freeman-Dyson and Wigner. And I just wonder if we basically have to think about a similar sort of classification for not just the Hamiltonian, but basically other observables, such as the spin in this case. But really, I was thinking about that for a couple days. So. Yeah.
So in your helical case, you had one sector +2 and one with -2. Okay, so those two mirror sectors completely decoupled, and so total Skermion number was 0 if you added them together.
Yeah.
Which means if you weakly couple them, the total Skermion number would remain 0. Do you think there might be another topological protection? This is 2 thing, for example, like there is in the topological insulators.
Yeah, so this is a great point. So another way
So
that
not churn number, but something else.
yeah, so this is a great point, and I guess I'm working a little bit on this right now. But of course, if you think of the many different kinds of just like electronic topological phases in equilibrium, and you think a bit more about the relationships between each of them, it already tells you where to look in basically finding other variants of this Skermion topology. Yeah, basically, you should anticipate something like this.
Okay, I guess in this case, because it was even, maybe that will never be an issue. I think you said
Yeah,
these
sure.
models was always even,
Sure,
so
I
it's
won't say
easy.
any, more. Yeah.
Yeah.
Um,
But one could construct another model where you had a log Skermion number where maybe you could have a so-called helical phase that was protected by Z2 symmetry.
yeah, I would say there are definitely other
There's no reason why
variants.
not.
What?
There's no reason why not, I guess.
Yeah, I guess our intuition from what we know about, I guess, topology associated with projectors definitely tells us that we should expect more of these, even at this level. One other quick thing I wanted to say, just because I remember someone being confused about this once upon a time. So I was telling you that the Skermion number can change via a type 2 phase transition. I was not saying to you that the total churn number changed via that transition. I have not observed that in these systems that I've considered. Yeah, I'm just reiterating. Basically, instead of just trying to tell you facts, I am also anticipating various misconceptions or misunderstandings that could happen.
So in the tenfold way, the classification really is based on things that or invariant under any deformation that doesn't close a gap in the energy. Okay, so clearly this is something different because it can change without closing a gap in the energy, so it's not part of the tenfold way.
Yeah, exactly.
But-
This hasn't been considered
Yeah,
before.
but yeah, I think I'm understanding what you're saying about the classification now, that you have to consider a different matrix or something that is.
Yeah, I'm not sure if
is
you should,
something giving the spin gap as its eigenvalues or something like this.
yeah,
can be projected
I'm-
somewhere, and then this should have its own tenfold way classification.
something like this.
Yeah.
I'm not sure, like maybe you could just think of the like operators associated with other observables. But a key point there would be that which symmetric space is relevant also, I think, depends on the other degrees of freedom, basically in the Hamiltonian.
And I think it also includes this issue that when you close the bulk energy gap, you have a something that's then not well defined in terms of eigenstates.
Yeah,
Hence, nothing is protected at that point. Yeah, very true.
So if this C prime,
yeah.
this is like a standard C3 that we have in the technical way, and then this it also has an extra action on the spins, right? There's some spin.
So you can really, basically, it's the C prime operator is the product of the C operator, a particle hole operator, where C squares to -1, and spatial inversion.
Do either of these things sort of do something to the spins?
I think the key thing is it forces the spin operators to take a certain form that leads to an associated non-trivial homotopy group.
If you need to have something that modified, you have like these standard symmetry operators that we're used to. Do you have to have like a modified one to get this in topology?
A modified one.
We have a modified C.
I really haven't had a chance to explore the other symmetries that could lead to non-trivial homotopy groups for spin. That's something that has to be explored.
Yeah, just going on from this, have you got any general insight into features of the Hamiltonian that might make it susceptible to having an extra topological feature? Or so far, is it just specific examples?
I don't think I have any, or any intuition about that, about when you should expect it. I think one thing, at least that I could say related to that is you may get some intuition by thinking about various generalizations of non-trivial homotopy groups for smaller matrix representations. So the idea is if there's some generalization of a homotopy group associated with smaller matrix representations, then you might expect this sort of topology for like subsets of your degrees of freedom of the ground state in that case. I think what I just said was kind of confusing, but like basically the point is like this SP2N over UN, if you consider the N = 1 case, it reduces to SP2 over U1, which is isomorphic to SU2 over U1, which is isomorphic to the two sphere ultimately. And so this gives us some intuition about why we might expect it to lead to non-trivial topology beyond just examining or successfully computing, I guess, the more general homotopy group.
This original symmetry isn't the symmetry of the Hamiltonian, correct? The SP2N. What you just said.
In this case, projectors are acted upon by that quotient, but spin is also acted upon by that quotient.
Okay, so they happen to have the same.
They happen in
that's
this case,
sort of-
which is a big part of
Yeah,
the
okay,
confusion,
They may well. have
the
already-
confusion that was associated with this.
Okay, so you have to think of the space the operators have to use. It requires some thought.
Yeah, I guess the key thing is maybe thinking just about the Hamiltonian is insufficient to fully characterize the topology associated with the Hamiltonian, basically.
Everything comes from the Hamiltonian, but they sort of see what you.
Yeah, I guess the key point is you seem to have to think about these other observables and the matrix representations.
Which may or may not
for
be
those.
real observables. There's nothing that forces them to be.
Yeah, I mean, we're always more interested in, you know, the most like physical consequences or
yeah.
experimentally relevant consequences.
But from the maths of the multi-beam, it doesn't matter whether they're a physical thing or not. Classification is based on.
Yeah, you're
is there a
right.
certain symmetry or something, whether it's.
Yeah, from the point of view of the homotopy groups, they don't care.
Yeah.
Yeah,
It's kind of interesting that like, I guess topological invariants, you want them to be able to smoothly deform stuff and to keep them the same.
you
But-
want them to be unaffected by
Yeah, yeah.
sufficiently small perturbations.
But so I guess the traditional Chern number only changes with the energy gap closing. So that's like one thing that affects it. But I guess here you've got two things that affect it. So
Two things that affect
so
what?
You've got the spin gap affecting it, and you've got the energy gap affecting it. But there's nothing you can define where just the spin gap, the spin degree of freedom gives you a single thing which is unaffected by the energy bands. But then affected by the spin.
I haven't seen such a case yet, but I guess one thing that yeah, I don't even know if it necessarily if it would, happen in this
I think
case.
it can. I think when the energy band's closed, then you've necessarily got an ambiguity in something.
I think the key point is in that case, the spin goes to 0 in magnitude.
Because
So you're kind of screwed.
well, it might or it might not be. It's just not defined because you've got two degenerate eigenstates and you fill one of them and you don't fill the other. And of course, it makes no sense to say you've got a choice because it is. Therefore, it can always change.
Yeah, but one thing I was talking about yesterday that's at least like somewhat related to what you're saying was I was thinking it might be possible to find a case where your homotopy group for the projectors was trivial in a particular dimension, but maybe you had a non-trivial homotopy group associated with some other observable, in which case you might only expect basically quantization associated with this topology associated with just a subset of the degrees of freedom of the ground state.
Yeah.
That would be a fun example to try to find.
Extreme case of it just being topologically trivial
Yeah,
in terms of the whole thing. It's being that it has to be because
yeah,
there's a symmetry that protects it. Yeah, that would be cool.
yeah, it'd be cool.
We have the time.
We still have 10 minutes if we have more questions.
Yeah.
We can also finish early.
Yeah, so you frequently refer to the topology of observables. But I thought the whole idea of topology in the context of quantism is the topology of the ground state wave function. And if I know the ground state wave function, I can evaluate all observables. So if it's a property of the wave function, I shouldn't have to make reference to specific observables. I should be able to just talk about the shape topology of the wave function itself. So I don't understand this extension that you're suggesting, that you have to refer to something else like spin, because everything is contained in the wave function itself.
Yeah, so maybe at least one comment that I can make as a step towards kind of addressing this is this example that happens for the strontium ruthenate type binding model, where you do not have a non-trivial homotopy group associated with the orbital angular momentum. And so you can think of having basically a topologically trivial like aspect of the system, a reservoir into which topological charge density, at least associated with spin, can just flow. And this may be part of the decoupling basically between the full, like I guess the projector invariant and the spin invariant. That's
The wave function knows about the spin as well as the angular. It contains all of that information. So you shouldn't have to refer to specific observables to define the topology of a wave function.
Yeah, but it can have more than one topological number,
Perhaps, but
which is, I think, basically what she's saying. That there's a churn number, but there's also a spin churn number or something like this. And whether these are quantized or not depends on the exact system. But, I mean, if you could find a complete set of topological numbers that characterize something, I'm pretty sure that's one of the open.
those are
questions.
response functions that reflect the topology of the system, right? And but the topology is something of the wave function, and the observables are manifestations of that topology. They remain the same so long as you maintain the topology in the gap system. So I must say, I think that either you've discovered a complete hole in the original tenfold way in which they missed the topology of the wave functions, or there's nothing extra. It's one or the other. Can't,
it's the first one.
okay, that's fine.
Yeah, the tenfold way characterizes a single topology that is well defined so long as the gap doesn't go to zero.
I thought it was supposed to characterize the topology of the wave function.
Like via a single number. There can always be more than one.
No, there was no notion of a particular number there.
A
It
single
was
number.
entirely defined in terms of the symmetries of the Hamiltonian, which determines the wave function.
Yeah, which then is given by a single topological number. It's a mapping from the wave function onto a topological number within certain symmetry classes. But for every symmetry class, there's only one number you have. And even, I mean, from the beginning of topology, we all knew that any object can be classified by more than one topological number. And it's an open question in maths to see can you find a complete set.
Okay,
I think
but
we just
that
never
would
thought
mean
of looking
that
for
would mean that the first possibility perhaps.
Yes, it is the
addition-
first possibility,
addition.
but the important thing is that this is not something that's protected by the energy method. It's something else that means that so smooth deformations that don't close the gap may change this topological number. So it's just not what they were thinking about at that point.
But it wouldn't be a robust feature of the ground state.
Well, if it's protected by some other gap, like a spin gap, it could be. You just have to know what.
What do you mean by spin gap?
Oh,
So
so
it is an energetic feature of an excitation.
okay, the spin gap is basically just the minimum magnitude of the ground state spin expectation value texture over the Brillouin zone. So basically, if your spin is finite in magnitude everywhere over the Brillouin zone, then your spin gap is finite.
Yeah, it's not.
It's just the magnitude of the spin.
It's a different definition. It's nothing to do with excitation. But it's, we call it what you want. It's a perfectly valid thing to say. It's just unusual to work out when that's relevant and when it's not. Which it's hard to get. Okay, any last questions? Yes. Okay, then perhaps you can have some coffee.